Okay, so let's get started. What I'm going to do today is have a few final thoughts on CPU scheduling. Remember last time we were talking about processor scheduling. I did a refresher on undergrad concepts in CPU scheduling, and then we talked about how Minix implements a 16 level priority scheduler. Few more things I wanted to mention before moving on. I'll do that. Then I'm going to say a little bit about IPCs and interrupt handling in Minix. There was a question, I believe, either last class or the class before on how messages work in Minix, because you encountered that when you did system call. So I decided I'll have a few slides just to address that specific question. Probably I should have discussed that when we did system call, but somehow I did not cover that material then, but we'll do that today. Okay? And then we'll basically continue our discussion from last time on process management. So we've done the scheduling part of process management. We'll talk about process creation today. Okay? And then we still have one more lecture on this, which is going to focus on the process manager itself, how Minix has implemented some of these concepts using the process manager. Okay? So that's really where we are in terms of the lectures on process management. But I do want to say one more thing about the slightly longer term roadmap. So if you remember at the beginning, I said that the course is going to include some coverage of Minix and Linux, right? And so far we only been doing Minix because that's directly relevant to what you're doing in your lab. But there is a mini course on Linux woven into this course. Okay? So next week we are going to do 2 lectures on Linux, okay? Which will basically be very similar to the concepts we have covered already. Okay? Linux architecture, Linux CPU scheduling. So you'll get a feel for how things are different in Linux versus Minix, and maybe why they made different design decisions and so on. Okay. Then we will resume our discussion of Minix for several more classes, and towards the end we'll do 2 more final lectures on Linux, which will again cover the rest of what we have done in Minix. So it's basically a 4 lecture sequence in Linux that we kind of retrofitted into the course discussion. Okay. So next week is going to be all Linux discussion, and then we'll resume our Minix discussion. And just to be clear, I'm going to be doing Minix. Our secondary instructor is going to be doing Linux. Okay, so that's the 2. Of course, neither of us are the Minix or Linux guys. Those are the real Minix and Linux guys. Okay, but for the purposes of this course, that's how you have to think of the 2 of us. Okay, all right. So that's the logistics, and then we will have more things to say. But let me just finish our discussion on CPU scheduling. Okay, remember I said I put this picture up last time, right? So that's the 15 level priority scheduler that does MLFQ. There were certain things I should add to that. The first of it is that not all of the CPU scheduling actually happens in the microkernel, because this is Minix after all. Lot of stuff has been moved out of the microkernel. Okay, so in particular, you will see that there is essentially a scheduler process there on layer 3. Okay, that's actually implementing most of the scheduling. There's a little bit of the scheduling that happens inside the kernel, and then it invokes the scheduler process saying now you can tell what process to run next, and that's the one that's going to implement much of the bulk of it. Okay, so it's a 2 so split into 2. It's not a 2 level, but it's just split into 2. Okay, so how does the user level do it, and what does it do? So here's the picture you want to keep in mind. Okay, but there is essentially a scheduling server like the process manager, like the file server. You essentially have a process that's entirely responsible for CPU scheduling. Okay? And the process and the kernel, they're going to interact in several ways. So there are 2 kernel calls, sysschedule and scheduler control, that are designed for the scheduling process to invoke the kernel service. And then there are several messages the kernel can actually send to the scheduler to tell it certain things have happened, right? Saying maybe you need to start the scheduling of the next process and things of that sort, or here the priority has changed. And so there are some messages that the kernel can send to this process. There are some kernel calls that the process can make. That's the interface. Okay? Now, given this interface, you can implement whatever CPU scheduler you want inside that process. Of course, the standard one implements an MLFQ. The same picture I showed you is actually implemented. The bulk of this decision making as the code actually sits in the scheduler process. Okay? Any questions on this? Because you are going to modify it, so it's better to pay attention and ask questions. Okay. So, some more details, I already mentioned some of this. So, there are two kernel calls, okay, the scheduler control and the schedule calls that are actually going to be used. Okay. So, essentially they are going to send messages to the kernel saying let us start scheduling a process, okay, or whenever the process that is being executed, its quantum expires, you are going to get a message back from the kernel saying run your function and decide what to do next and things of that. Okay. Now, the kernel itself does some work for you. The work of actually enqueuing, dequeuing process, etc., can be done inside the kernel, but the task of choosing what to run can actually be implemented in the user level scheduler. So, there is some work that the kernel will still do, but by and large the policy is in user space. Okay. Now, despite moving the policy out of the kernel and putting it into user space, there is still a small default policy they have left inside the kernel, okay, just in case if the CPU scheduler process crashes. Okay, then you are not going to be able to do anything. So, there is some default thing that will still take care of doing the basic stuff, while and the bulk of the work is actually done inside the CPU scheduler. So, that is what you want to keep in mind, because you do not want the kernel to not have a scheduler process if it crashes, and then nothing can run in the system, right. So, there is still a small policy that is in there, but most of it is handled by the user level process. There are some data structures there that I just added for sake of completeness. We are going to come back to that process table entry when I talk about process management later on today. Okay, so, I am not going to cover that table at the moment. Okay. So, I already mentioned this, but let me just skip that and instead say something different. So, the implication of running your scheduler in user space is that you can actually have more than one of them. Okay. This you will not see in a monolithic kernel. Essentially, there are kernels including Linux that have support for multiple CPU scheduling policies, but when you compile the kernel, you have to pick one. Okay. You say I want the kernel to be compiled with this policy, and that is the one that is going to get baked into that binary. Okay. So, the decision, so even if there is support for multiple, you choose that at compilation time, and that is what that kernel will run. Okay. In this case, because you have a user level process that implements scheduling, you can actually run more than one of them. Okay. And you can say if this is the process or this is the device, call this scheduler versus that other scheduler. Okay. So, you can actually have multiple policies and say for these class of processes use this, for these other class. So, how you decide this orthogonal? The point is you can actually do this on groups of processes or any other criteria on a user basis or whatever else you want to do, and say I can actually support multiple schedulers. Okay. The kernel will still do the basic thing, but then depending on what is happening, it might invoke one or the other. Okay. That functionality you will typically not see in a traditional monolithic kernel, because this now is saying that I can support multiple policies at runtime, rather than saying I have implemented them, you have to pick one at compile time. Okay. So, that is an interesting thing to keep in mind that Minix allows you to do. Of course, it has not actually been implemented in Minix. Minix has only one scheduler, but in theory you could actually add more. Okay. So, that is all I had to say about CPU scheduling. What I am going to do now is spend a little bit of time talking about interrupt handling and IPCs, because there were some questions about messages and how messages flow from when you make system calls and so on. So, this is some more Minix specific background on interrupt handling and IPCs, and then we will resume the discussion on process management. Okay. So, let me start with the IPCs. Okay. I am going to show a picture first and then come back to this slide. Okay. So, this is a picture taken from the book. Okay, it looks like a bunch of squares, but it basically shows you different message types that Minix will support. Okay. You will see that there are essentially 7 different types of messages that are predefined for you. Okay. And the messages basically differ in what they contain. So, this one, if it says I1, that says that is an integer. You can have a message where there are 2 integers and 4 pointers. Okay. Or you can have a message where there are 4 integers or 2 pointers. You can have one where there are 2 characters, 2 integers and 2 longs. Okay. So, they have defined some message types already. Okay. Of course, you can define new ones as well if you want to, but by and large I think you can make do with these because they have been used within the kernel for common tasks. Okay. In particular, where this comes into play is if you are implementing a system call, you have to use a message type. It is just good to just pick one of these, okay, and just use it rather than trying to define a new one and so on. Okay. So, depending on what kind of message you are trying to pass, okay, if it maps to one of these, does not mean every field has to be used, but if you can make use of that message type saying, okay, this one actually has a character array, I can pass a string into it, right. So, you can just use that type if you want to pass strings between processes and so on. So, there are these predefined ones, and my general suggestion is if you are using it for any message passing, for any code you write, try to stick to a predefined one and see if you can just make use of it. Okay. Adding message types is going to add more complication. Okay. But that is aside, how to use it aside, the thing you want to keep in mind is there are essentially 7 predefined message types. Okay. And then essentially what you are going to use is messages are sent using send, they are received using receive, and then there is another one called send, receive and notify. Those are the 4 calls that you can use to actually send messages back and forth. Okay. Typically, you may not use it, but and something you might invoke within the kernel or a system call will actually use those internally. But you can also use that API to send messages and receive messages explicitly. Okay. So 7 message types. Okay. So, the other thing is they are all a struct which is essentially a union of all of those types. Okay. For this you need to understand what a union is. This is essentially a concept that is there in C and C++. You may not find it elsewhere. Okay. So, essentially it says that you have a structure, okay, which has different fields, but it could act as one of n kinds, and here it is one of 8 types. And you can say now if it is a message of type 4, that struct will look like that type, otherwise it will look like something else and so on. Okay. So, it is a union of structs, but that is really not important. What you can simply do is you can define a message, and then there are all kinds of macros written to make things very simple. So, you can index a field saying message type M1, field 1 which is an integer I1. So, that essentially allows you to access essentially if you do M1 L1, it will basically give you that value. If you do M1 I2, it will give you that value. So, you can just access it as any struct and not worry about the subtleties, but you should know that there are subtleties in that, the way they have implemented it. Okay. So, they have tried to be very efficient in terms of memory use and so on by defining a somewhat complex data structure for messages. Okay. So, do not try to define new message types is the simple message you want to keep in mind here. Try to use one of these, life is much simpler. Okay. Now, if you want to actually go deeper into how IPC works, most of those are implemented in this proc.c. For example, you can see that there is a function called mini send, mini receive, mini notify. That is where all of the hard work is being done in terms of sending, receiving messages. Okay. The other thing you want to keep in mind is these are all blocking call. They use a rendezvous framework, which essentially means you are doing blocking, sends and receive. These are not non-blocking. So, if you send a message, the receiver is not ready, the sender will block. If the receiver is ready, the message is immediately going to be copied into the receive buffer, and then both the sender and receiver can continue execution. Okay. That is how standard synchronous sends and receives work, okay, in any message passing framework. You can also have asynchronous, but it is not implemented here. Okay. In general, message passing can be asynchronous as well. Okay. If you take a 677 class, we go into all of these concepts in a lot more detail there, but here you don't need to worry about that. You should just know that sending and receiving are blocking operations, okay, and then essentially you are going to use this simple framework of a send, receive, or notify calls. Is that clear? Any questions? Okay. All right. So, I am going to spend a little bit of time talking about some hardware concepts. I do not know how much of this you encountered in some other class, because part of this is actually architecture concepts and part of this is OS concept. Okay. Has to do with interrupt handling. Okay. The picture you see there essentially shows you how interrupts are handled on a Intel X86 processor. Okay. This one is a 32-bit processor, older processor, but the concept is very similar. Okay. Anyone has taken 535? Okay. Few people. Do you remember anything on interrupt handling? You're taking right. Okay. All right. So maybe you'll get to this at some point. Okay. So I presume all of you know what an interrupt is, right? Essentially, these are hardware can send a signal to the processor, which essentially interrupts the processor, which is why it's called an interrupt. The interrupt is typically sent in electronic terms by simply raising a voltage on a certain pin of a chip. Okay, so if you think of the voltage level being 0 or 1 in binary, okay, if the voltage is low, that means there is no interrupt. If you want to raise an interrupt, you simply increase the voltage on that pin to high, then the chip senses that you raised an interrupt and then does something. Okay. So for each interrupt that you want to handle, there is essentially a specific pin on a chip. So these arrows essentially are specific pins on a chip, and you can then connect peripherals or whatever you want that essentially use that interrupt to signal the processor. Okay. That is essentially a concept of what an interrupt is. Okay. Now you will see this in the Intel architecture, you can, or 32-bit Intel architectures, you can support 16 interrupts. Okay. So there are 16 pins there. In fact, there are two chips, a master chip and a slave chip that you see here. Okay, so that's the master interrupt controller. There's a say each of them do 8. Okay, so that gives us a total of 16, but in reality you only have 15 because the 0th interrupt is clock. Okay, every time a clock ticks, it raises an interrupt, and then the processor can do something, saying that the quantum expired, that something else needs to be done because there's a clock tick. Okay, and you will see that there are some very simple things that you can notice here. So interrupt 1 is keyboard. Every time you press a key on the keyboard, okay, that keyboard will essentially then raise an interrupt. Then the interrupt handler will run and figure out what key you pressed, and then that is how the machine knows what you are doing. Okay. Same is true if you are clicking on a mouse, you will raise an interrupt, except that that might go through the USB bus and a lot more complications there. But that is by and large the concept of interrupt handling. Yeah, from a hardware perspective. There is nothing to do with OS. This is all implemented in hardware. We will see what the OS does when an interrupt is raised in just a second. Any questions on interrupts? Is this clear? Okay, there are some architectural details before we get into the OS stuff. Okay, so I mentioned most of these. The only thing I didn't mention here is that when an interrupt is raised, okay, the hardware essentially also has a table where you can fill in entries of memory addresses. That is your interrupt vector. So as I had mentioned 2 or 3 classes ago, if you have interrupt 5, you look at the 5th entry of that table. That 5th entry will have a memory address. You go to that memory address and start executing whatever instructions are stored there. That is your interrupt handler. Okay. So there is hardware support for this. In fact, there is you can actually have a table of up to 256 entries. Minix uses 56 of these. Okay. And they are called, in Intel world, they are called interrupt gate descriptors, IGDs. Essentially, it's an interrupt vector, okay, table of interrupts where we can figure out where the interrupt handler is stored. Okay, so that's something you want to keep in mind as far as interrupt handling is concerned. So now let's look at a few details of how Minix actually supports all of this. Okay. Given that interrupt handling will be dependent on the processor, okay, because every processor will have its own interrupt handling capability. Some of the code in the kernel has to be architecture specific. Okay, it is not architecture independent. So this is the first time we have encountered architecture specific code. Everything we talked about so far, system calls and schedulers, they are not dependent on what the CPU type is. Interrupt handling has to be focused on what CPU you are trying to support. If it's an Intel CPU, the interrupt controller is called, the chip number is 8529. So essentially, if you go and look in the source tree, you will see that there's a i8259.c source file. That is where all Intel specific interrupt handling is actually done. Okay. If you want to support an ARM architecture, you will have to add a file that is specific to ARM, for example, Raspberry Pi or whatever type of ARM processor you want to support. Okay. Now, the concept is no different, it is just that it is specific to that architecture. So, that you have an interrupt vector there that has a 8-bit index, it allows you to essentially index into the table and jump to the interrupt handler. Okay. That is the basic concept. Okay. Now, Minix makes things a little more complicated. Okay. The reason being, Minix has pulled a lot of things out of the kernel and they are running in user space. In particular, device drivers are running in user space. Okay. And interrupts are used heavily by devices to tell the processor saying something has happened. Okay. Network packet arrives on your Ethernet card raises an interrupt. Okay. The driver for a Ethernet or Wi-Fi card is running in user space. The kernel is going to receive the interrupt, but it does not have the interrupt handler. The interrupt handler is in the device driver, so it's running in user space. So some extra work has to be done by the kernel to then invoke the device driver to then say this is the interrupt you want to handle. Okay. In a monolithic kernel, this would not be the case because the device driver is inside the kernel. Everything is in one address space. So you will simply look at the interrupt vector and it will be an address that is address that's in the user space or the address space, excuse me, of the kernel, and you just start executing the interrupt handler. Here, that's not going to be the case. You will have to essentially pass that interrupt on to either a device driver or some other entity, which is then going to handle the interrupt for you. So this is the additional work you have to do because of moving things out of the kernel. And you will see this is going to incur overhead. And this is why you start seeing things slowing down, because things that you could just implement as a code that is just part of your address space now essentially has become a message that you are going to send to a device driver to then go handle the interrupt. Okay. Yes, question.
In Minix, are the device drivers still considered part of the system level applications? User space is split into.
Yes. So the question is, are device drivers still considered part of the system application? They are indeed. So there are 4 layers actually in Minix. Everything that runs in layer 4 is a vanilla user process. Okay. And the lowest layer is the kernel, and then there are some layers that are specific to system processes. Device drivers are one of them. You will see that they are just right below the kernel priority. Okay. So they are considered to be system processes, even though technically they are user processes, but they are system owned user processes. Yes, question.
Does that mean for scheduling they run basically where the kernel runs in the MLF queue, like in the priority of the MLF queue, do they run where the kernel runs?
Okay. Question is, do they run where the kernel runs? If you look at this and what I said last time, the only thing that actually runs at the lowest priority level is the system and the clock task inside the kernel. Everything else is not running at the same priority, is running at a lower priority. That includes the device drivers. Okay. Having said that, the other thing I did say, that's the picture here, is the top 5 priority levels are essentially kernel and system services. So think of them as not the same priority level, but something close to the kernel. Okay. User processes are 7 and up. Okay. So priority 7 and higher. User system, the kernel is priority 0. 1 through 4 are device drivers and process manager and the scheduler and things of that sort. Okay. So not the same priority level, lower. But higher than processes, lower than the kernel. Okay. Any other questions? Okay. All right. So I am not going to spend too much time on this. You should know that there is some additional complication in how the interrupt handling works, but beyond that, it's still the same concepts. Okay. So the picture here shows you all the steps that the kernel has to perform in order to handle an interrupt, and I had mentioned this in the first class. I am going to show this picture just to make that more explicit. So, the device raises an interrupt that is going to raise a voltage on some pin that is specific to an interrupt ID. Okay, then that is essentially going to cause an interrupt on the processor. First thing that the processor has to do once it gets an interrupt is essentially save the current state of whatever is running on that processor, because now something else has to run to handle the interrupt. So, you save the state of the currently running process, all the registers etc. are saved, and then you basically index into that vector and then try to figure out where the interrupt handler is. Okay. Now, in Minix world, that address is going to be just a stub, because not the real interrupt handler code. It can say that this interrupt handler is actually in that device driver. So, that stub is simply going to then send a message to the device driver saying interrupt happened, and then the device driver takes over. Okay. Otherwise, it would be the actual code that you have to handle. So this is the flow of what happens. This does not actually show the interrupt handling. This is the book, but you can essentially see that you send a notification message to the device driver, it is going to do whatever it is doing, and then you restart the process. Okay. Now, system calls use a very similar process. Okay. In system calls, you are not raising a hardware interrupt, you are essentially raising a software interrupt. Software is a software that is sending a signal. It is not a real signal like hardware is actually, you do not change the voltage on any pin or anything like that, but you can essentially call a instruction that says there is an interrupt, a software interrupt, and then rest of the process is very similar. Okay, you are going to essentially index into a vector and then figure out what system call to execute and so on. Okay. Any questions on this? So, this is a little bit of background I wanted all of you to have, because you are after all implementing a system call. Even though you do not see any of this, you are not going to actually touch any interrupts or make a specific interrupt or anything like that. That is what is happening under the hood to execute that system call for you. Okay. Is this clear? Any questions on this? Okay. So, I am going to get back to process management. We had a bit of a digression because there are some things I just wanted to mention before moving on. Okay. So, let us get back to process management. So, I am going to start with another refresher, which is basically define for you concept of processes and threads and creation works. Look at the fork system call, which presumably you know if you took an undergrad class in OS. I will mention what it is and we will look at how Minix deals with all of these things. So, let us start with some very simple definitions. So, what is a process? Okay. So, I presume you know what a program is. Program is something that you write, it's code that you write. And then if you write it in some languages that are compiled languages, then you basically have a binary or an executable. Okay. A process is essentially a program in execution. When you execute a program, it essentially becomes a process in users in memory. Okay. So, this you should know. This is just a standard definition from an undergrad OS course. Okay. So, now what does the process contain? Okay. What is the definition of what is in a process? Okay. A process essentially has some memory allocated to it. That is called the address of that process. Okay. A process has state associated with it. Okay. What is part of the process state? Anyone remember anything from OS class? Yes. Registers are part of process state. Okay. Program counter, heap pointer. Okay. What about what the process is doing? Okay. That is also part of the process. Is it ready, runnable, waiting? All of those things are all part of the process state. Okay. There are other things that are also part of the process state, which is memory management information, what files are open. Okay. All of that is essentially part of the process state. Okay. Now, how does the OS keep track of all of this information? Anyone remember this? For every process, the OS has to keep track of those pieces of information. Okay. Okay, so you have to have a data structure which is called the process table. Okay, I'm going to skip this. This is just showing 4 processes executing sequentially. Okay. So here's a picture that just shows you the layout of a process. I already mentioned this before. Every process has 3 segments: the text segment which holds code, the stack segment, and the heap. Okay, heap is dynamically allocated memory, stack is essentially local variables and so on, and this is the picture you want to keep in mind. There's always the text segment. It's not going to look like that. You can't put source code in a text segment, but that's just a cartoon picture. And there's a stack that's growing up, there's a heap that's growing down. Okay, and there's a program counter that's keeping track of what is executing. So this is a sequentially executing process. Okay, it's essentially executing one instruction at a time. You can have loops and things of that sort. Okay, so now you will see here you already have the program counter, stack pointer. You have to keep track of where the stack is, where the heap is, where the process is loaded in RAM, and so on. Okay. Here is the other part of the process state that I was mentioning, that basically tracks what the process is currently doing. Okay. Typically, an executive process will be in one of 3 states, which I had mentioned last time also when we talked about CPU scheduling: ready, running, and wait. Okay. Ready means that it is ready and waiting for a turn on the CPU. Running means it's actually executing on the CPU. Wait means it's blocked on I/O. Okay. And then there are 2 other states: terminate, which means it's finished, and new, which means it just started. Okay. So it cycles through those states, but the CPU has to keep, not the CPU, the OS has to keep track of what state the process is in. Okay. All of this information is kept in a data structure called the process table, okay, or the process control block, PCB. Okay. So essentially, the OS have a data structure. For every process, there is going to be an entry. That entry has all of that information: priority of the process, how much CPU time it has received, all kinds of information is tracked in that process control. Given the amount of information you have to track in that data structure, as far as Minix is concerned, there is no single table that tracks it all. Okay. You will see that Minix actually splits the process table into 3 parts. Okay. There is essentially one part that sits in the process manager. There's one part that actually sits in the memory manager. Okay, and there's one that sits in the file manager or the file server. Okay. Because these are user level processes. Okay. So what we have done is, logically you have a single table, but physically you split the implementation of the table, and each process keeps that part of the table that's relevant to it. Okay. So that's the way you want to keep this in mind. So if you go in Minix source for the process table, you are not going to find one table that has all the information, because it's actually not stored that way. Unlike a monolithic kernel data structure, here it's actually split across multiple entities in the kernel. That's again an artifact of a microkernel architecture. Is that clear? Okay. Okay, so moving on, I'm going to talk a little bit about threads. We are not going to go. Oh, your question, yes.
It's about the process tables. How do they connect? How do if you have one process table, you can know which ID goes, like which you can see all the fields are connected. But when you have 3, how do you connect which processes
Okay.
have this?
Okay. The question is that if you had only one table, you would have an entry for a process. All the fields are in one place. If you have 3 tables, how do you connect up the information? Okay. So every process is going to have a unique ID, the process ID. So although it's not shown there, all of those tables have to actually have a process ID field in it. So the same process will have entries in all 3 tables. You index the process ID, you have the information for that process in that table. Okay. Any other questions here? Okay. So coming to the notion of threads, I'm going to quickly introduce this. You should know what it is. We are not going to spend too much time on this, because Minix does not have support for kernel level threads. So you will kernel at all, because Minix only supports threads that are actually done at the user level, okay, which we will see in just a moment. So what is a thread? What's the definition of what a thread is? Or if you use threads, what do you think they do? Yes.
It's kind of like a sub-process.
Okay, it's like a sub-process. What does it do?
It executes a function or something within a process.
Okay.
And doesn't create, so it's contained within its parent process.
Okay. Okay, we won't use the term sub-process, but what you're saying makes sense. So, essentially what I described, a process has an address space, and there's one program counter that's executing one instruction at a time. So, there's a single thread of execution that's we've woven through that process. Okay? But there's no requirement that there's one entity executing code in that process. There could be multiple entities that are executing code of the text segment. Each of the entities is going to be called a thread of control. Okay? So, essentially there are multiple threads of control that are sharing the same address space. Okay? The text segment is the same for all of those. Okay? So, each entity can execute any part of that segment, of that text segment. Any function can be executed by any entity in this case. Okay? Each process, each thread is going to get its own stack, because when you call a function, you got to expand the stack and so on. Okay? So, the stack is no longer shared. There has to be multiple stacks, one per thread. Okay? The heap, on the other hand, is going to be shared, because that's dynamically allocated memory. Okay? So, the picture you want to keep in mind, okay, is this one, okay, where on the to your left is a traditional sequential process. Okay? Single thread of control, one thing executing in that process at any given time. Okay? One stack, one heap, one set of registers, etc., etc. Okay? What is shown on the right is a concurrent process. So, there is a sequential process, concurrent process. Concurrent process says it has multiple threads in it. Okay? You will see that one has 3. Okay? You will see that each thread, okay, so what is not clear is there are no boxes here. This is essentially one text segment. This is the same code. Okay? But each thread has its own stack. It has its own set of registers that you share the heap and whatnot. Okay? So, this allows you concurrent execution of code within an address space. Okay. Let me now, so the same picture, I am going to just skip that for a second, show you the same picture I had put up before for a process, but now look at the thread. Okay, so, there are multiple threads here. In particular, there are 2. If you look at that, you will see that it starts 2 threads. This is for a producer consumer problem. So, they are executing within the same text segment. You will see there are 2 program counters, one for each thread. Okay, in this case, one of them is executing that function, the other one is executing the other function. Okay, there are 2 stacks. Okay, the heap is shared. Okay, there are 2 stack pointers, but single. Is this clear? Okay. So, does anyone remember the difference between concurrency and parallelism? Do multi-threaded program give you parallelism? No? Yes? Don't know. What is the difference between concurrency and parallelism? What's the definition? Before we ask the difference, what's the definition of concurrency? Yes, please.
Like multiple processors or cores or parallels, they're like
Yes.
running at the same time rather than just giving you a parent event.
Yes. So, concurrency, the definition of concurrency is it looks like there are multiple things executing within an address space. Okay? They are executing concurrently, okay? But that does not mean they are executing at the same time, because if it is a uniprocessor, only one of those threads can execute at any given time. Right? But if you have a multi-core system or a multi-processor system, you get true parallelism, where both of these threads can execute on 2 separate cores at exactly the same time. So, you get true parallelism. So, multi-threaded programs give you concurrency, but if you run that multi-threaded program on a multi-core system, you also get parallelism in addition to concurrency. Okay, so, you need to at least know these differences when you write threaded programs and so on. Okay. Now, very quickly I am going to talk about, so I mentioned this in the picture, I am going to skip this, talk about kernel level threads and user level threads. Okay. I presume if you remember anything from an OS class, you have heard of these terms. Okay. As the name kernel level threads suggests, Okay, the OS kernel actually has explicit support for threads. Okay, what does that mean? What does having explicit kernel support for threads mean? Yes.
Kernel knows like the number of threads and to schedule them.
Yes. So explicit support simply means the kernel can actually see how many threads are inside that process. There's 2 threads. Okay. So now that you can actually see how many threads there are inside that process, schedule them. You can, now the CPU scheduler is no longer choosing a process for execution, it's actually choosing a thread within a process for execution. Okay. Same CPU scheduler, you can have MLFQ scheduling, but you are now actually choosing a thread for execution. And when you choose a thread, you automatically pick its process for execution as well. Okay. Now we can talk about user level processes, or rather user level threads. Okay, as the name suggests, there is no kernel support for threads in user level threads. Okay, that Minix is in that category. The Minix kernel does not have any support for threads. Okay. Yet if you want to write threaded programs, the way you are going to do this is you write a library that provides support for threading. Okay, because the kernel has not supported threads for you. So you write a library that actually implements the entire concept of a thread for you. Okay. So now the kernel doesn't know how many threads are inside a process, okay, because it cannot see that there are threads in the process at all. It just sees processes. Okay. So the CPU scheduler is simply going to choose a process for execution. Okay, it's going to say let's execute process 5. Okay, then how do you decide how the thread gets scheduled? Yes.
The process can itself decide how it process.
Yes, the process can itself decide. So essentially, here is a picture that shows you what happens. So scheduling is now a 2-level decision. The CPU scheduler in the kernel scheduler, because in Minix it's not in the kernel. The OS scheduler chooses the process. Okay. When you execute the process, first the library runs, and there's a scheduler in the library that says which of the threads should run next, and then it chooses a thread for execution. Okay, so that's how you are essentially going to schedule threads in a user level system, thread system. Okay. Any questions on this? So the interesting thing about user level threads is each library can implement whatever scheduler it wants for its threads. Okay, if you want to do round robin in process A, you can do round robin. If you want to do lottery scheduling in process B, you can do lottery scheduling, because they are all implemented as a library function. Okay, you can have multiple scheduler, one in each process if you want to. Okay. Remember that in Minix you can do the same thing at the OS level as well, because I said earlier that you can have multiple schedulers executing in concurrently. Okay, which most other OSs don't do, but at user level threads can do that, and they often do as well. Okay, so now with that quick background, I'm going to show you a little bit of, you probably written some threads code. So there are 2 or 3 threading libraries that are very popular. There's pthreads. If you're in Unix world, you essentially write your threading code using POSIX threads, okay, in C or C++. If you're writing it in Java, you write Java threads, because Java has built-in support for threads. If you're in the Windows world, you can use the Win32 library. By and large, they all do the same thing. They allow you to create threads, delete threads, manage threads, use semaphores, locks, and all of those kinds of things. Okay. So here are some function calls which you have a question.
So I was wanted to know, like, does user level threads also allow us to support parallelism? Like, let's say we have.
Okay, that's a good question. I should have asked that question myself. The question is, does user level thread allow you to support parallelism? Not concurrency, mind you. Concurrency, of course, any threading package will do. Yes.
Well, unless the process gets scheduled by the OS on multiple cores at the same time.
Okay. So to get true parallelism, the process has to get scheduled multiple times, or not multiple times, on multiple cores. Okay. The OS doesn't know that the process has threads in it. In fact, the OS is designed assuming processes have no threads in it because it doesn't support threads. So the OS is certainly not going to schedule a process more than one thing because it thinks that the process is only one program counter. Right? So why would it schedule it? So typically in user level threads package, the kernel will not schedule a process on more than one processor at a time. So you are not going to get true parallelism at thread level. Parallelism, you can spend processes on two cores. So you will get process level parallelism. That's still a real parallelism, but not thread level parallelism.
Thread server or thread manager and like just put it into Linux and then just do it.
Yes. So question is, can you implement your own threads scheduler? So as you see in the slide, the people have done that because only way to support threads is through user level threads packages. There's a very lightweight library called mthread, which stands for Minix threads, that implements a POSIX like interface for threading. There's also a GNU thread, a pthreads, which is just taking the pthreads implementation from a GNU system and just porting it to this. So both of those exist. Okay, both do user levels thread management. Okay. Yes, question.
In Java or Python or things like that, are these how are these threads usually implemented? Like, is like for Java, would it be in the Java like? Is it somewhere in the Java virtual machine that like they translate these thread calls?
Yes. So the question is Java and Python is different because Python has kind of thread support, but really not that good, right? So as far as let's just take Java as an example. That's your OS. Okay? You have a process that's running. Nothing seems to work. Okay, so that's a Java process. That's your JVM. That's your code. Okay, so you have Java threads here. Okay. Now it's up to the JVM implementation to decide whether those threads are going to be user level or kernel level, right? If you write your JVM for a OS that has native support for kernel level threads, then the JVM should take advantage of this, right? So it can essentially map each of these Java threads to a kernel level thread. Okay, and then those threads are going to get scheduled by the kernel and you'll get true parallelism if you have multiple cores and all of those good things. But then you can also write a JVM for an OS that has no support for kernel level threads. In this case, we make the JVM implements its own user level threads package manager. Okay, so then it basically still supports Java threads because the Java interface is not changed. Java code has to run on any JVM, so it will still get threads, but they just threads. Okay. Same is true of any system, including Python. If you essentially port Python to a machine that does not have kernel level threads, any concept of threads have to be done at the user level. If you do, then you can use kernel level threads. Okay. There's one slide I did skip, which I do want to go back to, which goes back to this point, which are threading models. Okay. So the threading models there show you how user and kernel level thread differ from an OS perspective. Okay. The first picture here. Okay. So this essentially says user level threads get mapped onto one entity inside the kernel. This is user level threads because that entity is essentially a process. Okay. The OS is a process. The presence of threads in them, it only schedules processes and then that schedules thread. Okay. The picture on the top right is kernel level threads. Okay. That's a one-to-one mapping where every user level thread gets mapped onto one kernel level entity that one of these entities to run that user level threads essentially execute. Okay. So many to one to one, and then you can actually have others as well where you might have 4 user level threads getting mapped onto 3 kernel level threads, and you could also do, you can design your own mapping in your processing. This user level thread is doing important stuff. I create a special kernel level thread for it. These ones just share these 3 and things of that sort. Okay. So if you use the sophisticated feature of any threading library, okay, it will allow you to deviate from this model and do one of those. Okay. If you're in user level threads, that's what you're stuck with. You can't do anything. Okay. But a kernel level thread by default is going to give you one-to-one, but you can essentially do many-to-many. Okay. Yes, question. Okay, what's the benefit of doing many-to-many? So that is basically goes back to what work is each thread doing and how much CPU. If you essentially have the one-to-one model, that's the default model. Each of your threads is going to get scheduled at the same priority level. It might get the same amount of CPU time and so on and so forth. Okay? But maybe there are some tasks inside your application that are more important than others that might need more CPU time. So you might create a special just for them, and others get to share. Right? So if 4 of them share 3 of these, then the CPU time for these 3 is getting split across them. So in aggregate, each of them is getting less CPU time than that, for example. Right? So you can decide. So if you have a browser, for example, maybe the GUI thread is getting mapped to kernel thread for high responsiveness, but some background processing can be shared. And so you can decide if you want to deviate from the one-to-one. Okay, any other questions here? All right. So we did threads, and as I said, there's really none of this applies to Minix other than the user level concepts, because that's all that Minix actually has. Okay, you have a question? Okay. All right. So let's talk a little bit about process creation. Okay, so now we are getting deeper into the process manager. So you're going to talk about fork and exec and things like that, right? So what causes a process to be created? Okay, so in Minix or in any system, when you boot up your process, certain processes start running. Okay, that causes process to get created. Any process can create another process, and we'll see how that is done. Okay, user can submit jobs that create a new process. Okay, or you can essentially click on an icon on your user interface that starts a process, and so there are many ways you can start applications that start executing, and when they execute, they turn into a process. Okay? But what is actually happening under the hood to do all of those things? Essentially, you need to have system calls that allow you to create a process. Okay? Now, in reality, as far as Unix-like operating systems are concerned, every process, even on what I said on the previous slide, has to be created by some other process. Processes don't magically appear. Okay? So every process is going to that created that process. Okay? There's a parent-child relationship between any between any process in the system. Every process has a parent. Okay? The parent may have terminated, but when it got created, it had a parent. Okay? So then the question is, how does a process create another process? And this is done through a system call called fork. Okay, does anyone remember any of this? What does fork do? Yes, James.
So essentially, from this process is when they create the second process, and then the second process also starts immediately after the first.
Okay.
And then from that, they can determine whether there's a new full.
Okay. So fork essentially creates another process. Okay, so if you want to create a new process, you call fork, it's going to create a second process. Okay, when you just do fork, what is executing in that second process? Yes. Okay, so it's essentially an exact clone of the parent process. Okay, what fork is just doing is essentially making a clone. Okay, parent basically creates a child. The child looks exactly like in every single way, except that is a distinct process ID. You just take the memory and you essentially copy it, and then when you've created, the parent and the child look identical. Their program counters are pointing in the same place. Everything is exactly the same thing. Okay? And then beyond that point, the parent and the child can start executing different things within that process. Okay? Remember, it's a copy of that process, but they're not obligated to do the same thing anymore. I'll go into details of what fork, how it works, and so on. But then let me ask the following question: what's the point of creating clones of the same process? You will get hundreds of processes that all look the same. That's presumably not what you wanted to do. If you want to start a browser, okay, you click on that interface. Essentially, a graphical user interface has created a clone of itself, not started the browser yet. You understand my question? Because we said fork is a system call that has created a copy of that process. Suppose you want to start a different process. Creating a copy of an existing process does not let you do that yet. Right? So what will we do to address that issue? Yes?
The child process will call exec.
Okay, so child process is going to call another system call called exec. What does that do? Do you remember?
Yeah, and it just starts a new program. Like you pass it the arguments and the environment that you want to give it, and it just starts the program with that.
Okay. So when you do exec, you essentially specify the name of a binary or a program. Okay. So what exec is going to do is essentially going to that program, okay, and it's going to replace the contents of the current process with that program and start executing a completely new process. Is that clear what I just said? So you have process A. Yes. Okay, you call fork, creates a copy of itself, which is B. Okay. At this point, B just looks like A. It's not doing anything different from me. But what B can do is, once it continues execution after its creation, it can essentially call a function called exec, or rather a system call called exec. And then here you can essentially say /application/Chrome or whatever else you want to do. You can specify the name of a program, and then what that exec call is going to do is it's going to take that specified application from your disk, is going to load it into this memory region. Essentially, it will wipe out whatever is loaded there, which is a copy of the parent process. It's going to load that program in there and then start executing that program. Okay? So that's executing new program, two system calls, not one. First to create a process, and the second to execute something different. Otherwise, it's just going to execute the same thing as the parent. Okay? So an exec, as you can imagine, go to as pairs. Okay, so the essentially process creation is a two-step process. You could have said, why did you do this? Why couldn't you have just pass the argument to fork and let it create a process and load that program from the beginning? You could have done that. This is a design decision the OS designers did when they invented Unix, and 50 years later, okay, you have to make two calls to start a process, not one. Okay, first to create a new process, then to execute something different in that process. Right, so this is simply a design decision. There's no real reason you may want to do this, because you could have simply done that in one step, but that's not how it works. Okay? Okay, so now with that in mind, let's go and look at some details of how fork. And this is incidentally how your shell is also going to work. If you have a command line prompt, okay, you type a command, your shell is essentially going to do a fork, is going to create a copy. Then in there it's going to call an exec and just pass the string or whatever you typed, and then that starts executing that command. Okay? The shell is going to work the same. Lots of other things do exactly this. Okay, so here is essentially some C code that shows you how fork is going to work. You will see that you will basically call fork here. Okay? At this point, this process that was executing essentially creates a replica. Both of them look exactly the same, which is both of them have executed until this point. Okay? Now, the way you start, the child can start behaving differently from the parent is through a mechanism that fork provides. Okay? When fork returns after it has created a copy, okay, the return values are going to be different in the child and the parent. Okay? In particular, in the parent, the fork is going to return an integer, that's the process ID of the child. So if you created a new process, ID is 50, fork will return 50. Okay? But in the child, it's going to return a 0. Okay? So if you want to write code where you want your child to behave differently, you should just take the return value of fork and say if the return value is 0, so you basically write an if statement. So if the return value is 0, you go into the if and then you start doing something. So your exec typically is going to be inside the if here. Okay? Because you can't just have a fork and then an exec, because then the parent will also call the exec. Okay, remember that. You don't want the parent to change its behavior. If the parent is shell, it has to stay as shell. It's not going to change. So you only want the child to call the exec, not the parent. Is that clear? All right. So if you have learned this in OS, it should be very clear. If you haven't, then this is what you need to understand. Okay, that you call fork, and then you want to make sure only the child calls the exec, not the parent. The way you do this is you check the return value of fork. The OS guarantees that the return value, the value of fork in the child is going to be a 0. So you say if fork has returned a 0, go ahead and exec. Otherwise, in the else, still in the parent. Okay, so this is the parent code. So the child executes this, the parent executes this beyond the fork. Okay, so that's the main difference between how the child and the parent are going to execute. For those of you who don't know this from an OS class, are there any questions? This is a subtle concept you need to understand, because you will be using some process management soon as well. Okay. So here is the same thing shown in a picture. Okay, what I drew here is slightly better picture there. So you will see after the fork, you essentially have two copies. Okay, both program counters are essentially pointing to fork. Now in the child, when you go to the next statement, what is returned here is a 0. In the parent, ID of the child. So if you basically look at this and test it in an if statement, you can make the child do different things from the parent. And hopefully the child is going to call an exec. Okay. So here is a picture of what Minix is going to do for us. Right. So here we have A and B, two processes and the OS loaded. Okay. A is going to call a fork. You will see that you created a copy of A. Okay, so that's A's child that you see here. So this is after the fork. You see that there's a copy of A here. Okay, that's an identical copy of A. Looks exactly the same. Okay, then if A's child calls exec and starts a new program, okay, then you will see that that program is turned into C, because that's executing something else at this point. Okay, its size could be different depending on whatever that program is. You may change the size of the stack, heap, text segment, everything could be different at that point. Okay, any questions here? All right. So now let's go back, and those are the concepts that you learn in a OS class, but now let's look a little bit more into how Unix is actually going to, or rather Minix is going to do this. Okay, so those are the steps that if you actually go and look at the do fork system call or kernel, those things happening in there. And I encourage you to actually go look at this. The first thing is going to be process table full. Process table is full, you can't actually invoke a new process. Okay? Typically, a process table shouldn't be full, because you can always expand the size of the process table, but you run out of memory or something like that. Right? So then you are going to return an error. Okay? You can create a new process. Okay, you are now going to allocate memory for that process. Okay, so first thing is you got to allocate some RAM. Right? So in this case, the same amount of RAM you allocated to the parent gets allocated to the child. Then you are going to essentially copy whatever is in the parent's memory into that allocated region. So you just make an exact copy. Okay. So then you are going to find a free process slot. You are going to allocate that memory region, not allocate, enter that memory region into the process table. You are going to find new process ID, sequentially increment process ID. You are going to essentially tell the kernel, here's a new process that we created, here's an entry for it, and so on. And then tell the kernel, here's the amount of memory allocated, and so on and so on. Okay? So essentially create an entry in the process table, allocate memory, copy the contents of the parent into the allocated region. At that point, you created a process that's a clone of the parent. Okay. Remember that the parent is not executing at this point in time. Okay, so the contents of the parent's memory is not changing while you make this copy. Okay, why is that? Yes.
Because it's waiting for a reply from fork.
Okay, because you made a system call. You called fork. Okay, what does a system call do? It suspends execution of the process and goes to the kernel to execute that system call. So by definition, your process that invoked fork has no longer is waiting for the system call to finish. So it's safe to copy its content and assume that it will not change while you make this copy. Because the memory region can be large. You can have a 500 MB. Okay, you can have 2 gigabyte process. You have to actually make a real copy in this. And technically you don't, because you can use smarter things like copy and write. All of that copying, so on. So, but you know that the process memory will not change while this is happening. Okay, so it's safe to do these things. Okay. So very quickly, exec is not very different. So in this case, you already created a copy. You are trying to start a new program. So you're going to check, is that program, the string that you've passed, is it executable? Do you have permissions to execute it, etc. You're going to allocate new memory. Okay, and release the new memory, because the size of that new process could be completely different from the initial size of the parent process that created it. Okay, so you have to delete and allocate. So you see that this is somewhat wasteful. If fork had allowed you to create a new process in one step, you wouldn't actually have to allocate new memory and release it, because you made a copy, threw it all out, started a new memory region, right? So, but that's how it works, right? So then you essentially create a stack, you create a heap, set up essentially some permissions for that process, and then tell the system that OS that now this process is ready to run. That new process is going to start executing from the beginning, because a new brand new program. When you first create a child, it did not start from the beginning. It actually started from where you are at fork. You just started executing from the middle, right? But this is now running exec, so you are going to start from the beginning. Okay, is that clear? Okay, any questions on this? Yes.
Why does it need to allocate new memory? Why can't it just use the old one?
Okay, good question. Why do you need to allocate new memory? Why couldn't you use the old one? Okay, technically you could, but we don't know that the new program or the new process you're starting needs the same amount of memory as the old process program. So in this case, you can see this picture, right? So this is the size of A, whatever was executing. So when you made a copy, that's the same size of memory you get in the child process. Now you start exec, and that process that you start needs a lot more memory. So it's much easier to deallocate and reallocate. So that's essentially why it's doing that. And you're anyway scrubbing whatever was in that process and replacing all the stack. Everything is erased and reset as it is. Okay, but the size doesn't have to be the same. It will be different, which is why it's better to actually allocate a new region. Okay, yes.
Kernels support kernel and will they execute different threads of the same process on multiple cores?
Are you asking a fork specific question or independent?
Yeah,
Okay.
This is a prerequisite for my fork question.
Oh, I see. Okay. So if you call fork on a multi-threaded process, child process is also going to be multi-threaded. Okay. But if one of those threads calls an exec, then all the threads are gone. Started a new process. But you don't have to call exec. As you know, you can just do a fork, and all of those threads can start continuing or can continue execution.
If there's one thread executing on one core and another thread calls fork, they share the same memory space. So when it does that copy, isn't that still potentially being modified during the copy?
Okay, that's a very good question. Okay, the question is, if you had a multi-threaded process and you had true parallelism, if one kernel thread calls fork, okay, and then you start making a copy, but there's another thread running somewhere else that is just changing something, mucking around with memory, then you are going to get a problem, right? So that's, I think, a good point. So this is why you need kernel to do safe things, right? So you basically, when you are doing a copy, you can actually mark the memory region as read only and do things like that that allows you to do copy, right? So you have to do this. If you have multi-threaded kernels, lots of things have to change. You have to make the kernel itself thread safe. It's called a re-entrant kernel. But there are lots of other problems that can occur. What if two processes call fork on two processors at the same time? Okay, that data structure, that process table will need a lock at this point. We didn't assume it was locked because you are mucking around with entries. So lots of things have to change immediately, okay, and including how fork gets implemented and so on. Right. So unicore system much easier. Multi-core gets complicated, including scheduling. The kernels are written. There's more locking in the kernel. All of our system calls are implemented, change, etc. And we have not looked at any of those things. We are just doing the basic things here. Okay. Any other questions? All right. So let's just stop here because kind of run out of time. We'll continue our process management discussion in 2 weeks. Okay. Next week, Linux mini course is starting up. Okay. Just something to keep in mind.